So, we will continue with the class, coming to the fourth lecture on dynamics of ocean structures. So, in this lecture we will talk about more on different kinds of compliant systems, the tension-like platforms, spar, semi-submersibles, new generation of offshore structures, and some very brief introduction to coastal structures. In the next lecture we will discuss about some of the different varieties of coastal structures and how are the structural action has been defined for different kinds of loads. So, for the understanding of what we discussed in the last lecture, we said that compliant towers have high degree of flexibility. Flexibility is high. The advantage of this flexibility which is introduced from the form is mass is lower, stiffness is also lower. Now, mass getting lowered helps me to install, makes it economical, makes decommissioning simple. Stiffness getting lowered makes the structure flexible, by the virtue of which it will attract less forces, and most importantly the natural frequency of the system is beyond the bandwidth of natural frequency of the waves or frequency of the waves. Waves, wind, it is not in the bandwidth of this. So, these two characteristics have been achieved by selecting a form in the design stage itself which makes the structure compliant. Compliant means the structure moves. When the structure moves, the structure encounters a relative motion. Relative with respect to what? Relative with respect to structure and waves. So, this relative motion reduces the response because the forces are reduced, and therefore, ultimately the benefit what I get is structural responses are reduced. Now, what is the great advantage of structural responses getting reduced? What are the structural responses? One classically may be the stresses, bending moments, axial forces, torsional moments, etc. Now, there is no great advantage if these are all reduced, because anyway I am using a steel which is having a very high value of Fy. So, I do not gain any great benefit by reducing these values on my structural members, but what I am talking about is the responses reduced in terms of the motion, that is, for example, surge, sway, etc. To understand the responses, we must know what are the different degrees of freedom which a floating body may have. If you look at the 3 axes, let us say I am drawing all the 3 axes here, I am putting them as x axis, putting this as y axis, this as z axis. Let us say this is my origin, where I am going to measure my response, where all the responses are practically 0. So, any response which is along the x axis is termed as surge, which we all know. Any response along the y axis is termed as sway. So, this y matches with this y, you can easily remember this. Any response which goes along the z axis is heave, and any rotation, you put your thumb towards the axis, remaining 4 fingers will show a direction of rotation. I am marking it in that fashion. This becomes roll. Similarly, I show my thumb here, this becomes my pitch. I put my thumb here, this becomes my yaw. So, all these are specific names given to directional displacements. All these greens are specific names given to rotational displacements. On the other hand, surge, sway and heave are displacements along x, y and z axis, whereas roll, pitch and yaw are rotations about x, y and z axis respectively. So, it is a specific name given in the literature. So, what we call them here is the degrees of freedom. We will talk about this in dynamics perspective later. So, these are the degrees of freedom. So, since we spoke about the response in terms of the structural motion, we wanted to know under which degrees of freedom a compliant system will have lower responses and why. So, if you put a floating body, let us take for example the articulated tower. For example, the articulated tower, which is also a compliant system, which we discussed in the last lecture. So, I have a tower, the tower has a top side, we are not drawing the top side detail. The tower has for example the mean water level where it is being installed. The tower has a buoyancy chamber, the tower also has a ballast chamber, then the tower extends, subjected to a pinned connection, maybe a hinge here, a hinge here. There are hinges here also, we are not talking about this for the right at the moment here. When I have a hinge here, as we have seen, when the structure is subjected to any wave action, which is a lateral motion, the structure or the tower has a tendency to swing, which we call as either a surge action or a sway action, depending upon whether the wave is acting along x axis or along y axis. Okay. So, this will create a pendulum action because it is a hinge here, the structure keeps on oscillating. As we have quickly seen what happens to the buoyancy chamber, look at this portion separately. Now, the force is acting from the left to right. I have a buoyancy chamber which is initially vertical. Now, I have a buoyancy chamber which is tilted. It means if I draw an horizontal line, the immersion in this side is more than the immersion originally I had. Therefore, there is a shift of buoyancy from the center towards the right. Agreed? I call this as my buoyancy force, for example. Of course, there is no change in my W, right. So, this is what I call x bar or y bar depending upon is it sway or surge. This produces a lever arm, this gives me a anti-clockwise moment which opposes this force action and the structure comes back to normalcy. Similarly, if the wave force is acting towards right to left, same thing reversely happens. Okay? Is it clear? But there is a demerit in this kind of platform is that the restoration of this happens depend upon the volume of external submergence or additional submergence given by the buoyancy chamber. So, this action is very fast, okay. That causes lot of uncomfortability or discomfort to people on the board. It means compliant towers do not have control on surge motion, sway motion and sometimes yaw motion also, that is rotation about the vertical plane in plan. Okay. So, these degrees of uncomfortability or discomfort caused to the people working on board has got to be addressed in the form. So far it has not been addressed. So, people slightly worked much more on this and derived a new form which they call tension leg platforms. A new form which people said, okay, let me have a new structural form, the tensional platform. If you want to understand the block diagram of a TLP, the block diagram of TLP looks like this. I have a floating body, a 3-dimensional body. The original idea of this floating body in this structure was to keep the whole system above the MSL and introduce a separate buoyancy chamber which will restore the action. That has happened in guy towers in terms of guys, in articular towers in terms of buoyancy chambers. But in TLP what they did is they immerse the floating body itself in water. So, the MSL is somewhere here. Okay. So, if you want to have a large volume of submerged area, it is proportional to the weight, is it not? If you increase the weight, then all those advantages what ATs had in terms of installation, commissioning, decommissioning, cost, all were lost, is it not? Because if you increase the weight, then you will be imposing some extra penalty towards the increase in weight in terms of these points. So, they have got to be addressed. So, what they said is I will make the system whose W, whose weight is much lower than the buoyancy force. So, I will make the structure very very light. So, when I achieve this in my form, I am compensating for those concepts which have been earlier derived in ATs, because now I have a light structure, I am not increasing the mass, I am making it flexible because it is anyway floating. So, I am maintaining that K integrity, stiffness integrity. So, whatever advantages I had initially from the design of this form is transferred technically to this form by keeping the weight of this form much lower than the buoyancy. Now, the problem comes, how do we install this, because the buoyancy force will always act in the direction opposite to that of the weight of the structure. When the weight of the structure is balanced to buoyancy, exactly structure will float in any draft you want. If the weight is much lower than the buoyancy, when you start putting the structure on sea for floating, the buoyancy force will simply push the structure up, is it not? It will not exist there, right. So, they need to have some system by which you want to hold it down. They introduce tethers. People sometimes call this as tendons. Non structural engineering idiots will call this as cables. So, it is up to you, you want to name it in what form. So, teethers, tendons are the technical name given to this, nothing but they are axial loaded members which are nothing but a form of taut moved cables. Taut, it is not tight, taut moved cables, but they are specifically named as tendons or teethers. Can you recollect, this name is also given in one of the similar structure on land based design. What is that structure? Tendon. Very good. Pre-stressed concrete also has this name. So, it generally when you evolve a new form, people give associate certain terminologies to those members which are becoming slightly unique and which becomes common in many of the literature, right. So, tendon is a term given to pre-stressed members, the axial forces transformation members in steel in a pre-stressed concrete structures. Here these vertical members are called as tendons, these are nothing but actually cables. So, now the essential function of this teether or set of teethers is to pull this down, okay. So, they will be always have to remain in tension, is it not? I want to pull this down, so they should remain. I think we all understand how to mark tension and compression in a given axial member. Many people have this confusion, let us quickly eradicate this confusion. Many people have this confusion, plus minus confusion is still there till your death, right from your day of birth to civil engineering, but anyway this confusion will also remain. I have a member, I have another member, this is let us say joint A, there is somewhere joint B here. I want to mark the member FAB, force AB in the member, I get an answer as FAB as tension. How do I mark? You must always associate the arrow from the joint, okay. It is not towards the joint. If I say this member is tension, from the joint put the arrow. If I say the member is compression, put the arrow towards the joint. So, this is tensile and this is compressor, okay. The member pulls the joint, therefore, the member is under tension. The member pushes the joint, therefore, the member is introducing compressive force or compression, okay. So, now I have, let us understand this, let us come back here. So, they will be in tension. So, I am putting the joint arrows away and away, so they are in tension. Now, the design is very interesting, W plus T should be equal to FB, is that right? Because W is acting down, T is also acting down in this case. FB of course we all know it will an upward force, right. So, the difference between W and FB is compensated by T. Now, interestingly, the moment I said W is much lower than FB, you can expect the value of T which I call as axial pretension in the teether. Literature specifically addresses this as T naught. Why this naught has come? Because it is initial pretension. Now, you may wonder why this term initial has come here. Initial is a pretension set in the cable or the teether to hold the structure down, okay. Now, since the difference is very high, this T naught is expected to be a very high magnitude, okay. When a very high magnitude of T naught has got to be imposed on a wire or on a cable or on a tendon or a teether in a hostile environment where I want to install this, how do we install this? I cannot have a big workforce which will go down to the seabed and keep on pulling the cable. I cannot install a complex machinery at the sea floor at a depth of 2000 meters, 1200 meters, where the workforce or the machinery will be holding the teether and holding it down, cannot do that. Very simple, what they do is all these members should be made void, hollow inside, keep on filling ballast material in this, keep on increasing the weight very high, tow it down, put it at the side, release this water or release this ballast material, that tension will be transferred to the cable automatically. okay, that is the installation process. Anyway, we are not worried about that in dynamics class, but still one should know how this comes up, okay, that is how it is installed. Now let us quickly see, when I have a platform like this, remember very carefully, my structural system is only this, these are all nothing but cables and tethers. There is a similarity of this system in guide towers also, you would have seen guide towers also had mooring lines, okay. So only my system is this. This is also a structural member of a TLP, no doubt about that, but my form is only this, my mechanism is this. Now when I apply a lateral force to this system, as we applied it in articulated tower, what will happen to a TLP like this? Which are those degrees of freedom which I will now get an advantage? Okay, that is our focus now, is it not? So let us quickly see that, that is what we call as TLP mechanics. So I have a TLP, the water level is somewhere here, I apply a force or the wave action is applied onto the system, the TLP moves this way. Now there are two questions I want to ask you. Number one, what is the guarantee that the hull or the form remains horizontal? Because an articulated tower, but for the absence of articulation near the deck, the hull would have been inclined also, okay. What is the guarantee that I have the superstructure which is remaining horizontal here? It means these connections should remain pinned connections. Now I have a question again here, do you want these connections to remain pinned? These connections pinned, is it? Now what is the axial force imposed on a cable when it is a pinned connection? Infinite magnitude, is it? Infinite magnitude. This is the important point where articulated towers had a problem of failure, is it not? If you recollect the lecture last time, we said these are the points where the tower, if at all may fail, it will fail at these points. So they have become fixed connections here. It is nothing but, it is not a member, it is only a tendon. It is not a member, it is only a cable or a tendon, it is a mooring. Like for example, what was the connection of a mooring line in a guide tower at a touchstone point? Was it hinged? Was it hinged? It is fixed, because we are having a lead anchor, drag anchors, etc. We are having a weight also, counterweight, it is completely, it is more or less fixed, it should not move at all, is it not? Cable should not get lifted up, right. So there, so one great demerit of AT is, by putting an articulation at the bottom which was imposing a fatigue failure on the joints and becoming a critical point in the design, was eliminated in this form by making it fixed. The motion what the TLP makes in the direction of wave or force is what we call offset, and the motion what TLP makes in the direction of heave from the original position to the final position is what we call set down. Now interestingly, everybody will agree to me that when an horizontal or lateral force is acting onto the member, the structure moves, I can say the structure is surging or swaying, etc. So to restore the structure back, I do not need a hinged connection here, the cable is already in high tension, the cable will start pulling it back, and the horizontal component of this force will counteract the wave action. Of course, the vertical component of this force will add to the weight, which will balance the additional buoyancy created by set down. So, it is a very interesting mechanics. So, commissioning and decommissioning becomes very simple. Only thing what I have got to do is I have got to play with this connection and either ballast or deballast it if you want to install or uninstall it. So, it is very simple. Now, interestingly, look at this form. This form has no proportion with respect to at what depth this is being installed. This can be even 1 meter, 1000 meters, this can be even 1500 meters. The only difficulty you will have is the tendon length will be keep on increasing. You will be designing it only for weight versus buoyancy, and we all understand buoyancy depends on the submerged volume and not on the water depth, and weight of course depends upon the plant dimension, which is depending upon the function of the platform. So, I can put this platform in any depth I want. So, it has become depth insensitive. Is that clear? So, the form has become depth insensitive. Now, by this form it has got a very great structural advantage in dynamics. What is that advantage? It has got a very great structural advantage in dynamics point of view. Let us see what is that. There are 6 degrees of freedom which just now we saw. Okay. I will group them in a very interesting way: surge, sway and yaw. I am grouping them. There is a reason why I am grouping it like this: roll, pitch and heel. For our recollection of understanding, because it is a class after 2 days and Monday 8 o'clock is always a cursing class. Okay. People do not want to come at 8 o'clock. In fact, people do not want to get up at even 10 o'clock also. What they wanted is 2 things. One, the moment you get up you should go to CD. CD is coffee day. After that you should go to D, dating. Okay. After that you should go to sinus, that is sleep. So, in between S is missing, that is study. So, getting up in the morning, because coffee day opens only at 11, it is very difficult. We are not supposed to have the class at 8 o'clock because coffee day does not open at 8. So, it is very difficult for people to answer a question quickly. So, surge is displacement about x axis, sway is displacement along y axis, yaw is rotation about z axis, roll is rotation about x axis, pitch is rotation about y axis, heave is displacement about z axis. Okay. I am grouping them. It is not that I grouped it, the form itself demands this grouping. See how? Look at this body once again, look at this mechanics once again. When the TLP is subjected to lateral forces, surge is the motion what you have in the direction of wave, sway is the motion which is normal to the direction of wave, and yaw is the motion which can occur when you look at this in plan, when you look at this problem or the form in plan. This may be the wave. If the wave comes at an angular direction to the platform, there is a possibility that the platform may even rotate about the z axis. Okay. So, these are all what we call soft degrees of freedom, highly flexible. They are very highly flexible and they are soft degrees of freedom. Now, there is a reason why these degrees of freedom have been kept soft in the form. Can you tell me this reply for this question? Why I want to select these 3 degrees of freedom and keep them as soft in dynamics perspective? What is the necessity? We are talking about advantage and compliance structure. compliancy means movement, movement means softness. So, these are the ways by which the platform will respond to the wave action, right. Either they will move horizontally in x along y or y z, rotation about z axis. If you oppose this, then the platform will become rigid, is it not? So, I do not want to do that, I want to make it soft. On the other hand, the rotations of these about x and y and movement about z axis along z is restricted. So, they become rigid or stiff. Okay. There are reasons why I want to make these degrees of freedom stiff, because I do not want any vertical movement of the platform along z axis. There are two reasons for this. One, my cables will be imposed directly an axial tension additional to what is happening in the mechanics. Okay. So, this may cause what we call pull out of the theta. So, I do not want that failure to happen, I want to restrict the heave motion. Okay. Number 2, physically, psychologically you will understand, if you are made to move horizontally in x and y axis, gently you can manage. If you have been asked to move in the z axis constantly, even for a small magnitude, you will get tired. Any person who is on board, when subjected to vertical motion constantly, okay, he will not be able to work on board. Third reason, any movement on heave will affect my buoyancy force directly, which will again affect my T naught, and this kind of dynamic change in T naught may cause a fatigue to the theta. So, I want to avoid that. So, I have made this as stiff degree of freedom. Now, rotation about x and y are kept normal and very less, because they are rigid degrees of freedom, because I do not want any discomfort to people when the platform rotates about x and y axis for operational safety. The moment I say these degrees of freedom are soft, the time period of these degrees of freedom are very high. They range from 60 to even 110 seconds. Okay. Frequency is inversely proportional to T, so they are lower frequencies. Okay. That is why they are soft, means highly flexible, whereas rigid degrees of freedom we are stiff, the time periods of these are very low, they can be anywhere from 2 to 5 seconds. I am talking about the time period. Now, what is the common time period at which these waves will hit the structure? Let us take for example Indian ocean conditions or Indian coastal conditions. It varies anywhere from, yeah. Now, there are many answers, we can start giving numbers from 1 to 100, I think it will not cross 100, but at least people who have studied naval activities and ocean engineering, they will limit this 100 to 20. So, it can vary anywhere from, let us say 6 seconds to 12 very odd 15 seconds. Now, there is an advantage, my bandwidth of excitation periods are well separated from my structural periods. So, the dynamic response of this kind of system has got to definitely will be out of resonance, because the band periods of my force is separated from the design in terms of its degrees of freedom, is it not? So, there will be no near resonance response which is activated in the system because of the wave action, but the difficulty is with the wind action, this may not be the case. Now, you may wonder, sir, how I can design a platform for both wave and wind action? Any international code you pick up, the international code says when you consider both of them simultaneously, you must always consider only a percentage value of both of them, not 100%. For example, considering wave and earthquake, it is wave action plus 30% of earthquake only, it is not 100%. So, your design will still remain safe. So, any structural system or a form which has two distinct division of degrees of freedom is what we call hybrid system. TLP is a hybrid platform. TLP is the only platform in offshore structural systems which is hybrid. That is why they are very popular. They have been installed many numbers of platforms in different parts of the country, in the world, and so on. So, these are some of the components of a TLP: the drilling, dry trees, quarters, columns and pontoons, and of course the tendons. So, we will quickly browse through this. Design concept is buoyancy exceeds its weight. We already discussed that. Weight is much lower than buoyancy. The excess buoyancy created is balanced by pretension in the taut moved cables. Okay. Taut mooring are otherwise called as tension legs, because they are always in initial pretension. Generally these are tubular members or wire ropes. TLP is a unique type of platform because it is having horizontal and vertical plane different behavior. Highly flexible in horizontal plane, because you see all these degrees of freedom are related to horizontal plane. I pick up a plane which is horizontal, this is surge from your end, this is sway, and this is yaw. Okay. All these happen on an horizontal plane. So, it is highly flexible in an horizontal plane, whereas heave motion is a vertical plane, roll or pitch, all this happens about a vertical plane. So, it is very stiff about the vertical plane. So, such a combination is what we call as hybrid systems. Okay. This is achieved not by the wave action, it is achieved by the form. We are talking about the evolution of different kinds of forms of offshore structures on dynamics perspective. Remember, we have never addressed anywhere here the cost or anything related to the action, because I want to reduce the forces on the member, etc. All we are discussing is about the principles of dynamics as applied to the structural system, which is deriving benefit from the form itself. Okay. So, it is a dynamics perspective. So, how pretension is imposed on the teether? As you understand how it is imposed on a guide tower. Okay. There is a fair lead point, through which the cable passes and goes to the hull. There are lot of rocker mechanic systems kept on the hull on the top, which will keep on winding the cable and keep on imposing pretension to the cable. Similar way it is done here. We are not anyway talking about this application technique here. As I said very clearly, simply by ballasting and deballasting I can impose tension to the cable. Okay. So, commissioning and decommissioning becomes very easy, not that easy as we are saying here, but it is not as complicated as we are thinking about it. Okay. It is comparatively simple with respect to all other forms which you have so far seen. Okay. So, that is the TLP mechanics here. You can see the offset and the set down here, and that is a schematic diagram which has already been explained here. I showed it because that looks better than what I have drawn here. So, these are some of the classical TLPs have been constructed. Enough literature is available in open source, you must see them. 1400 meters capacity, already we know what do you mean by cubic meter of oil, what are the GDP, etc. Neptune TLP 2007 constructed at 1300 meters approximately. So, all these are deep water platforms, 50,000 BOPD, etc. The other kind of platforms is spar platform, which is also having a similar response behavior to that of TLP, but of course it is not an hybrid system where distinctly two sets of degrees of freedom are separated in the form. It is not there, slightly different, but spar can get into deeper waters compared to TLP, and they are contemporary to each other. Okay. It is like two regional languages in a given in the same country. Hindi is a national language as well as regional language in many states of the country. So, we really do not know whether English is better or Hindi is better. Okay. So, similarly spar and TLP. Spar also has classical advantages in terms of its structural form, It consists of a single large diameter vertical cylinder which is supporting the deck. I will show you a photograph followed by this. The cylinder is weighted at the bottom by the chamber filled with denser material, that is how the spar is being installed. This provides better stability for the spar platform or the cylinder against lateral action of wind and waves. Spars are actually anchored to the seabed by the way of spread mooring system, either with a chain wire chain or chain polyester chain system. We are anyway not talking about the construction part, installation part of it, that is anyway will be discussed in different course. Here we focus only on the structural action derived in dynamics perspective. So generally they are preferred to be anchored by a spread mooring system. There are different kinds of layout of mooring lines. There are three types of spar existing: the classical spar, truss spar and the sail spar. I am quickly defining them. Classical spar has got a cylindrical hull with a heavy ballast at the bottom of the cylinder. Truss spar has a shorter cylinder called as an hot tank. These are all available in the standard literature, you must have studied them already in different courses. So my insistence is not towards you to memorize this, but you must understand the form very importantly, which I will follow after this presentation is done. The most common type of spar is a truss spar, and of course your sail spars also have large central cylinder surrounded with small cylinders of alternating lengths. This is another spar platform what we have, Perdido spar. You can see the spread mooring system which can be seen in this photograph here. The advantage of the spar system is it goes deeper than TLPs because the cable or the tether cost is far relatively becoming inexpensive in the system. It goes around 2300 meters. Constructed in 2008, polyester rope mooring was used, constructed by a company by name Technip. Horn Mountain is another spar. You can see the central sail spar here, it is not a truss spar. You can see the topside complication remains as same or as simple as the earlier platforms. The only design alternative here is the sail spar has been the other structure has been replaced by a cell at the center. The advantage what spar claims is, with respect to other platforms, an operational advantage is that all the drilling risers and lines will get through the spar, they are protected from the wave action, whereas in TLP they are exposed. For example, I have a moon pool here, the drilling unit is here, the drilling risers are exposed to wave action, whereas in spar does not happen. So that is the advantage operationally what people claim, the spar is better. It is better inspectable because you have a cell spar, you can get in through the cell and inspect it. Maintenance is far superior, therefore it can go for deeper waters. The other kind of form what I am just discussing it here is semi submersible. We will talk about the dynamic analysis of floating structures at the next module. So we should have an idea about semi submersibles. You must have studied this very quickly. I will go through this. It is one of the oldest offshore exploratory rigs, typically operate in wetlands, but the question is they are meant for exploration, therefore the water depth is not very seriously high. They include posted barges, bottle types, arctic types and inland barges. A semi submersible rig floats on water surface and moves from one drilling type to another one. So flotation analysis becomes very important in this kind of structures. I will show you a very interesting let us say the free floating analysis what we did for a commercial rig in South Africa. So we have the full design perspective, there is a new kind of a semi submersible and drill ship which we did. So we will show you at the next module where we talk about dynamic analysis of floating systems, how it is done and which software has been used, etc. We will discuss that. It is another important semi submersible constructed Blind Faith, installed in 2001, etc. It is a production platform. The next one is an FPSO, which we all know, floating production, storage and offloading. We will just quickly go through the slide, it is not of very important to me, but still essentially used for offloading of crude oil to the shuttle tanker. FPS stands for floating production system, whereas FPSO stands for floating production storage and offloading as well. So an universal term being used by supported by the sea floor, and included will be the TLP, spar, semi submersibles, all actually are floating production systems as we saw in the classical definition. So, we will talk about FSOs also very briefly, floating storage and offloading. There is no production here, production is on a different platform, it is associated with a production unit, and FSO is also a kind of platform. They are actually existing tankers have been converted as floating structures, which is essentially used for storage and offloading only, not for production. So, production is done by a different platform, they have been associated with these platforms only for storage facilities. So, they are used to store the crude oil, then ship it to the another location for processing. So, it is a functional platform, it is not a platform meant for production drilling. FSO, so FPSOs again, these are all floating kinds of systems which also include what we have as TLPs and spars, etc. So, they can be as large as, it is about 183 meter long, 62 meter wide, very long FPSO. Generally these are all existing vessels being converted for this kind of purposes. Plutonio is a very famous FPSO being commonly deployed. We will quickly look at the mooring and station keeping, because we will do an Arcaflex analysis later in the next module. So, one should know how do we do by a mooring analysis. So, there are two options exist for an FPSO to hold it down in position. People have studied about dynamic positioning systems, we will not discuss that in detail here, but I will just give a very brief outlook on DPS when we talk about this kind of installation systems later. So, generally this DPS. DPS is a very famous term all over India now, but still you can also use satellite or the thrusters can be positioned to control their motion using the GPS techniques, etc. So, this we mainly use for station keeping, which we see here. So, the mooring lines are essentially used to keep them position restrained when they are under operation. What we are focusing here is the new generation offshore structures in 2 minutes from now. Now, we have evolved so far different kinds of offshore structural system, where we saw how the geometry was taken as an advantage in the design itself. Okay. So, let us talk about new generation structures. Down the line, the first will be the buoyant leg structure. So, essentially I am talking about the buoyancy force. So, BLS are very important new phenomenal structures which have been meant and designed for offshore production, okay, in deep waters. Triceratops is another new form of structural system. We will look at each one of them separately in the next module. We have to study dynamic analysis of different kinds of platforms, fixed platform, jacket, etc. We will discuss about this in detail. We will derive the stiffness matrix and mass matrix of these structural systems here. We will show you how the dynamic analysis can be done. I will show you the results here using some standard software what we did. So, these are all research based platforms. We will talk about these forms, how they have been arrived when we move to the next module. 3 leg TLPs, TB TLPs, that is tension based TLPs, non ship shaped FPSOs, etc. So, these are all new generation platforms which are actually derived an advantageous form based on the structural action or the dynamic action under the lateral loads. So, in the next lecture we will talk about the coastal structures and their structural action against the lateral loads. Do you have any questions on this lecture? I will be happy to answer you. Any questions here? I have a tutorial I will show you in the next lecture. We will have questions on all these. All these are self learning exercises, we will not evaluate them, there is no need, because you will anyway copy either from my notes or from anywhere else. So, you are self evaluating. The questions which will be given you in the examination will be all from a non standard books. So, this is all learning process, you must learn. If you have doubt, please ask me here. The doubts cannot be put as answers to the questions in the examination. whatever we discuss here only will be asked in the exam, that I am sure, but the only difficulty is whatever I discuss I will certainly ask in the exam, that is the problem. So, how you have understood, how you have encrypted and decrypted I do not know, because my handwriting is excellent, it is state of art handwriting. So, how you have understood and how much you have understood, that too early in the morning or late in the afternoon I do not know, there is flexibility is very high and so on. So, if there are no questions we will stop here.